you simply say we have z variables here, and we have some analytic function here. And if we substitute, so if this is disk and this is some region gamma, if we substitute, consider w of e to the I alpha, and alpha runs from 0 to 2 pi, then this complex variable runs around the given curve. As I said, I'm going to give you some relevant examples. So what the theorem says, basically it's a Riemann theorem, that such conformal map always exists. It's another matter how to find it. And there are very powerful method. Basically, the method for finding this conformal map is to use a superposition of some known maps. Let's look at the examples. So let's start with something very simple. Let's consider the map let's add 1/2 here. What would you say? What it maps to? Suppose we take a disk, a unit disk, and what is the output? The input is the unit disk. What is the output? First of all,
everything but the unit disk, maybe. So you go from having everything magnitude less than 1 to everything magnitude greater than 1.
Say it again.
Is that a 1 over z and not a 1 over 2?
Let me help you a little bit. So let's substitute z e to the I alpha. We get w of z is cosine alpha. And so what would be the output? What kind of domain gamma it describes? As you see, it's something very simple. Simple but tricky. Maybe I was unfair starting with it. It's the simplest algebraically, but geometrically it's... So what would you say? What happens to W? What you have to check is what alpha runs from 0 to 2 pi, and W runs around some closed curve. What is this curve? Well, let's draw the W plane. And what really happens here is that as alpha goes from 0 to 2 pi, cosine alpha goes from -1 to 1. So if you mark points here, -1 and +1, you will get an infinitely thin thing. The disk was compressed. It was just pressed from all sides, and it formed this singular line. It's now suppose I want to. I'll do a slightly different thing now. Let's take W. Again, I will substitute. Now, what should I, if I have this function? This, by the way, has a special, these maps, they are really practically used to calculate airfoils, flow past airfoils. And they're called Zhukovsky function. So let's see what kind of thing we will get. W will be e to the I alpha plus lambda e to the minus I alpha. And that would be, let's put 1/2 here. So it's 1/2. 1/2. It will be 1 plus lambda cosine alpha plus 1 minus lambda I sine alpha. Now, what would be your guess? What kind of object we will get? You see, when lambda was 1, we have no imaginary part, and that's why we got this purely real strip. Now, this time we do have imaginary part, and we have to decide. This thing describes some curve on a plane. Pretty simple curve, actually. What do you think?
An ellipse.
Yeah, it is an ellipse, because it simply means that if you take real part divided by 1 plus lambda square plus and this is the equation for the ellipse. So what happens is that we have this ellipse, and as lambda goes to 1, it actually shrinks to this line. Now, if you try again using the same tricks, the same function, but you have z minus a here, then you get the shape which is which is used to approximate airfoils. You get something like that. When we generally have this thing, of course you have, well, I will tell you how to use it for the flow. So far it's purely geometrical thing, or mathematical thing. Now there's one very simple thing. We want, this one more mathematical comment, we want some attack angle for the airfoil. So we would like to rotate it a little bit versus the flow. How to rotate it using this formula?
Just multiply it by a complex constant.
That's right, yeah. Just by some phase, e to the I theta, you will just rotate it and you will have attack angle. But we now to finish the logic, I forgot to finish the logic, how it is related to the solution of this equation. Very simply, you take, you have this map, W of z. It maps the disk onto the region gamma. Now, let's consider the complex potential, which is just complex potential for the disk, but calculated. So the relation is complex potential for the domain gamma, which depends on W. So here we have Z variables, here we have W variables. And they are simply equal to one another. So you can easily check that I leave it for you to play around with. you check that the condition that the velocity is tangential. If it is tangential on a disk, it will be tangential on this domain gamma. So the normal velocity will be 0. So all you have to do is to have two things to calculate the flow. You need to know the correct complex potential for the disk, and which is rather easy. But you also need to know the conformal map, and that is not quite so easy. But so far it's nice, clean math. Now we're coming to some dirty physics. Namely, when we look at this, so we easily get the map of this for the flow of this type, just by rotating this picture. And it's actually, I many times told you that complex numbers, complex phase is a rotation. It's associated with a transformation of two-dimensional rotation, and with conformal maps, this phrase becomes literal. It's literally multiplying by e to the I alpha. We rotate the picture. Yeah, but there is a problem. When we solve this equation, we have of course, we have to solve this to find z of w, and z of w will be singular at this point. There will be a singularity. It's actually not hard to see how it appears, but you just solve this quadratic equation, and z of w will have a singularity. As a result, when you differentiate to find the velocity, you have velocity in the region gamma is d phi gamma over dw. And when phi gamma has a singularity in w, as it did here, we have an infinite velocity diverges. There is a square root like singularity, and it's not really clear at the first glance what to do with it. You see, when you have a singularity, it means that your assumptions are incorrect near the singularity. For example, we saw that you, for instance, have viscosity, and this viscosity, although negligible everywhere, near the singularity becomes relevant. So we have to think a little bit about this. And the resolution of the puzzle is highly non-trivial. So non-trivial that it may be even wrong. Namely, let's return to the case of a disk. Actually, well, I probably have to say that people, of course, compared these things with experiments, and they found these prescriptions which we are going to develop more or less from the experimental data. What I'm going to say is that the solution for the disk is not really unique. So we return to the case of a disk again. We checked that if we have the Laurent expansions, all terms like 1 over z to the n, they don't work. They don't give the correct boundary conditions. However, there is one thing which works. Let's add the logarithm of that. You may say correctly that it's the logarithm of that is not a one-valued function. It's a multi-valued function. How can it be? We know that all physical quantities are by definition univalued. We want to know what is velocity at a given point. And now I am suggesting to you that we have some logarithm. If you rotate, if you return to the same point, after closing the circle, what happens to the logarithm?
Increases by.
Yes, we simply say if you multiply that by e to the 2 pi I, it's equal to log z plus 2 pi I, by definition of the logarithm. So we have.
What about the boundary condition infinity?
Yes, well, I'm going to address this. Well, in any case, I can even answer this right now. It's clearly subdominant to this term. So it's the boundary condition at infinity is not to worry about. But multivaluedness is something to worry about because physics should be univalued. So what do you think is the resolution? Try to resolve this. Think about what is really physical and which quantity should be univalued and which not necessarily. The point is that I'm trying to make is that the complex potential itself maybe not, it's not what we measure. So it may not, it's okay for it to be multivalued. So, but what should be univalued? V, and is it? Well, look at this formula. If you differentiate it, this thing disappears, and log z ddz is simply 1 over z. So we have velocity, but before I go further, so we found one thing. We will see in a moment. It's trivial that it satisfies this condition. That's pretty obvious. But one might have an unpleasant feeling that maybe we can add something else. For example, we can try logarithm square or something. Why logarithm square will not work?
Its derivative still has a logarithm.
Exactly. Its velocity. It's the only thing which works is this thing which for the velocity we have. Well, now, how to see that this condition is satisfied? Trivially satisfied. You multiply it by that, and it's purely imaginary. That's why I put I there. So, and what is the meaning of this thing? What kind of thing we added, actually? So what happens around the disk? How would this velocity distribution alone, it should remind you of something. We actually encountered with it. What is it? The velocity, which is in complex notations, is I kappa divided by 2 pi z.
The velocity in a vortex?
Yeah, it is as if we have a vortex located here, so that the circulation, the point of the matter is that the circulation of the velocity, which, by the way, in real coordinates would be just epsilon alpha beta, it will be proportional epsilon alpha beta x beta divided by x squared. Its circulation around this body is equal to kappa. So we add a circulation. Moreover, and we have still an unknown constant, the value of the circulation. Moreover, when we have the flow becomes, it actually changes. So let me draw the picture here. There are two special points here. This is the flow without added vorticity, without added, circulation. What is the velocity at those points? It's 0. These are called the stagnation points. Those stagnation points, and you immediately see that without circulation, the stagnation point, as you see from here, is simply z equals 1 or minus 1. So you just look at this expression and to find the stagnation points and solve the condition that this is 0. Okay? And that when you add this kappa, you see that the stagnation points are not plus or minus 1 anymore, because you have also this term. You have to solve the quadratic equation to find the stagnation points. And the flow becomes something like that. It becomes asymmetric. And so on. And moreover, in this case, in this symmetric picture, the pressure here and here, what can you say about it?
Sorry, pressure where?
Well, okay, let's have the picture of the pressure. So this is with circulation. So where the pressure is somewhere large, if you look at the boundary of the body, the pressure will depend on the point of the boundary. So where is the pressure large, and where is the largest and the smallest? Where we have the largest pressure here, for instance?
Beneath the
Why?
beneath? Because you have more.
No, I mean, I'm now looking at this picture.
This one.
Oh, sorry, yeah, sorry. At this picture. So what can you say about the pressure in this picture?
I think you would have to be maximized to the left of it when it comes in contact with the.
So what would you say about the pressure here? Let's compare 4 points. What would you say at the pressure here, 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 here?
So on the left you would have a high pressure.
Yes.
And on the right you would have zero pressure.
You mean here on the right? Okay.
And, above and below you would have something.
Okay, and how you came to these conclusions?
Because if you have a front of fluid and when it hits the side,
I understand what you're saying. You mean that it seems that it's hit directly here, but it's rather dangerous. We need some equations to verify this intuition.
Bernoulli.
Huh?
Bernoulli.
Bernoulli? What would Bernoulli tell you?
The pressure is maximal at the stagnation.
Yeah, and it is the same here and here, because there are two stagnation points. It's a bit counterintuitive, but Bernoulli knows better. And so it's the pressure here and here are actually minimal, because velocity is all velocity goes because they have large velocity, and indeed we have this thing. Now, if you think about this, if you look about this picture, you realize that from Bernoulli again, that the picture is completely symmetric. You see, if you look at this formula without it, it's symmetric z to minus z. So, which means that there is no lift force here. Lift force appears when you have when the pressure here is larger than the pressure here. So the lift force appears only because of the circulation. And actually we can write down quite easily the expression for the force in terms of kappa. It's basically proportional to kappa. Kappa being a circulation and this. But now we have to resolve two problems, which people did. It's actually a lot of struggle with this. It's in the beginning of the 20th century, with the development of aviation. People learned a lot of tricks, both mathematical and empirical. And the most important thing they realized that it's because of the circulation we get the lift force for the airfoil. All right, but how to find this? You would believe how they found the prescription for finding the circulation. And the prescription is this. The prescription is that you have this sharp edge here with singularity. You can find the value of kappa by simple differentiation of these things. So what you have to do? This is the expression for the velocity on a disk. Now we apply Zhukovsky transformation, which is this. Maybe it's spelled. And you calculate, so for that you have to solve this quadratic equation and find z of w, and on the rear edge it has a singularity depending on kappa. For a particular value of kappa, the coefficient of, I will not go with the algebra here, but for the particular value of kappa, the singularity vanishes. And it's a postulate called Zhukovsky or Chaplykin condition, that you define kappa, you calculate kappa from the condition that on the sharp rear edge there is no singularity of the velocity. And there is no justification of this, I must say, except empirical. You cannot derive it from the basic formulas.
If
Yes.
if you find kappa like this and then you do a different deformation, is it true that regardless of the deformation you never have singularity anymore?
Well, the statement is this. You take this particular shape, you obtain it with conformal mapping from the disk, and you calculate velocity here. It's only when this velocity does not diverge, it does not diverge only for unique special kappa.
Yeah, no, but my question is now, suppose you do a different conformal mapping and it
Yeah,
has a
well,
singularity.
then if I have, yes, then you can calculate whether it depends on some.
My question is whether
Yeah,
kappa is
whether for some arbitrary conformal mapping.
Yeah.
Yes, there is a statement that the singularity, you can analyze the distribution of velocity near this sharp rear edge, and you will find that whenever that basically it is the same as here. So as a result, you
There's
get only one edge. Yeah, no. Actually, it's an idealization. You can say, suppose we don't have sharp edge, then you just calculate circulation numerically. You have to solve the viscous equations, and there are some empirical tricks, empirical formulas, but there is no, to my surprise, actually, although people worked almost 200 years on this, there is still no analytic derivation of this value of the lift force. You just do it by means of these tricks. Well, but it's for engineers, it's fine because they have their own empirical formulas which work. But for a theorist, it's a bit unsatisfactory. Anyway, I just don't want to go into this. As you can imagine, it's a very complex subject with plenty of numerical simulations and windpipe tunnels and so on. A lot of experimental data are used here. And basically, there is the statement is that when the airfoil begins to move, it sheds off vortices and acquires a circulation, and this process of shedding off vortices and acquiring circulation continues up to the point when this becomes non-singular. So that's in comparison with beautiful, clean, complex analysis, it's a bit looks a bit dirty, but many things do. Still, it's very useful prescription. All right, we have to move from this. I just wanted to give you a spirit of this part of the subject, and we now introduce viscosity. By the way, before, as usually when I try to leave some subject, I remember lots of interesting things about it. Namely, people numerically saw how this circulation is formed here by vortices shedding in various directions and so on. Turns out there is also a mechanism for the wings of insects when they fly. People manage to measure vorticities which they generate when they start, the wings start moving. And the geometry and everything else are quite different there. But still, circulation generates lift, and that's it. And that's probably the main lessons which I want to leave from here. All right, now we have to introduce viscosity seriously and consider viscous effects. Yes.
At the level of when you're not considering viscosity, then it doesn't matter if the cylinder is rotating or.
It does not. Yeah. It's when with viscosity, of course, it will be very important. But well, there's also accepted if the cylinder is charged, for instance, then there will be some. There are some interesting things. Well, okay, the physics is too big. I just wanted to mention that there is something very interesting when they have a dielectric cylinder rotating. If it rotates, if you throw, say, a sound wave or electromagnetic wave on it, it becomes amplified. You get out more energy than you put in. This is called superradiance. Exists in many parts of physics. Interests me very much now, but but if I start discussing this, we will never finish. All right. So viscosity. Well, first of all, we have to rewrite the Euler equation in a slightly different form. You see, when we have a continuous media, we saw, in the case of mechanics of particles, we saw that the action, we have conservation law, and I remind you, we make a time-dependent translation, or we have gauge a translation group, and we get some expression called P multiplied by A dot. And we concluded from this that the momentum is conserved, and so we got the Noether theorem, which tells you that symmetries are related to this thing. In the case of continuous medium, the Noether theorem looks slightly differently. We already encountered with it. Namely, we looked at the continuity equation for the density. It looks in the form not that something is zero, but that there is a current. There is a density and a current. And conservation of this quantity means the continuity equation, like that. I give you a simplest example. Suppose we have the action, we have the position, the function y, which depends on t and x. We looked at it in one of our examples. And we have the action, which is y dot square minus yt square minus yx square dt and dx. Generally, we expect the variation of the action to be something like that. We expect it to have the form of the current. We now make gauge symmetry transformation which depends on t and x together. And from this, so we have, let me call it I, I includes time derivative and space derivative. And from this we conclude that time derivative of the time component minus plus minus x derivative of the x components is 0. So the natural generalization, for instance, here we have a simple symmetry which we can look at, y to y plus a. You see that if we vary this, we get yt delta yt a dot minus yx ax, and this is equal to 0. So we have the momentum current, momentum density and momentum current, and they satisfy the continuity equation. You can also have the usual time translation related to energy, and we get, in this case, if you make this time translation, you will check yourself that we have energy and we have the current. So energy, we have energy density, I would say. What do you think will be the energy density for this system? And the energy current. So this is a continuum limit of the system of harmonic oscillators. So what suggests what would be for harmonic oscillator? We have the something like omega square y square for the action. And what is the energy for harmonic oscillator in these terms? If the action is this. I hope you can see this. Let me write it down clearly. S, it's a y dot square minus omega square y square. That's the action and integral over dt for a single harmonic oscillator. And I'm asking a trivial question. Now you go through all these transformations. What is the plus sign, right? So we have energy here, which is y dot square plus omega square y square. And now what would be, now make a natural guess. This term is analogous to this one, and so on. So what is the energy density?
So just yt squared minus y, or plus yt squared.
Yes, yes, that's the correct expression. And if we calculate, and once again, if we integrate it over x, it will be total energy, it will be conserved. But continuity equation is a stronger statement. It is the statement that not only the total energy is conserved, but that locally energy is transferred, is epsilon dot, of course, is not 0, but it can be interpreted as a flow, as a flux from the given region. So we have we looking for the, well, I think I will do this. It's pretty simple. Let's write down epsilon dot. We have ytt plus yx yxt. We have, we substitute now the equation of motion is the wave equation. Ytt is equal to yxx. So we get yt yxx plus yx yxt. And as you see, give me the last transformation, which is natural transformation of this expression. It's something, there is one nice thing which can be said about this combination. For that you should remember what we expect to get. We expect to get a continuity equation, and we will. How? The continuity, expecting to get the continuity equation means that epsilon dot, what it means in general terms for epsilon dot, when we say that we have
Negative divergence.
it should be, yeah, it should be a divergence, negative, positive, depends on the convention, but it should be a divergence. Do we have a divergence here? Divergence in this case is just x derivative. Look, it's just dx of yt yx. So the energy flow, we have energy density and energy flow, which is yt yx. And we have epsilon dot is and that's a very general situation. And as I said, the general prescription, the generalization of the Noether theorem needed to derive such equation is very simple. Before in the ordinary mechanics, we said, let's make parameter of the group, of the transformation group, to be let's make them time dependent and calculate the change of the action as here. I call this gauging, not it's people call it gauging. And now we also make gauging, but with A, which depends on x and t. And in this way, we obtain the structure of continuity equation. Okay, now we want to rewrite the Euler equation as it is possible to rewrite them as a continuity equation. One continuity equation we already have. It's just this thing. And this is mass conservation. In principle, we should have equation for energy density. We don't know the current here yet. And we will have, more importantly, we want to have a continuity equation for momentum, for the momentum. So what is the momentum density? So once again, the continuity equation has two pieces, the density and the current. And now I'm asking, what is the momentum density? And then I will ask you next, what is the momentum current?
Is the momentum density just yt?
No. I confuse you. this was just an example, not Euler equation. It is related to the Euler equation in Lagrange coordinates, but now let's go to the Euler description in which our variables are the alpha, rho, pressure, and so on. And I want to derive, I want first to identify the momentum density and then to derive the equation for it. Just think physically, what is the, it's simple. It's rho v alpha, yes. So we have, interestingly, here rho v alpha was the current. Now we have to derive another equation which begins with a d dt of rho v alpha. So that was the the alpha momentum density of the alpha component of the momentum. There are three different momenta, and all of them satisfy the equation. So what would be the structure we should be looking for? What should be the flux, the current? I'm not asking at the moment, I'm not asking concrete expression for the current, but just the general structure, how many indices it has and so on. What these indices mean. So we will calculate it explicitly, but before calculating, let's think. So this is the general structure, so to say, or this is the general structure. That time derivative of the density, time derivative of momentum density should be related to something, to the current, to the divergence of the current. So but the puzzle here, which we have to overcome, is that it has the index alpha. So what kind of current we have? And before we dealt with the continuity equation where it was a scalar quantity. Now it's a vector quantity. And the interpretation of the current, it's amount of here. It's amount of mass moved in a direction alpha. Now try to generalize it here. Yes, actually we need something. Some quantity called this thing, called it has the name of stress energy tensor, sometimes it's called energy momentum tensor, and it has two indices, 3 by 3. So how would you interpret the quantity? So T alpha beta is equal to something we should find. What is its physical meaning?
Each component of momentum goes into each of the three directions?
Yes. It's the flux of the alpha component in beta direction. Exactly. And now we'll do a very simple thing. One can do this using Noether theorem, but it's more complicated here. The simplest way is simply to use the equation, the two equations. That's one Euler equation, and then rho dot plus d alpha rho v alpha is 0. And you see now it's pretty straightforward. It's just almost obvious. The equation tells you multiply it by v alpha. Let's call it beta. And add them together and see what happens. Again, I think I will not do the algebra. I will leave the algebra to you. And what we will get is the time derivative of rho v alpha is equal to d beta t alpha beta, where t alpha beta, actually you can figure out what kind of structures could appear there. Partly looking to this equation, partly thinking in general. You can actually more or less predict, it would be another derivation of the Euler equation. What is T alpha beta?
Rho v alpha v beta.
Yeah, it will contain almost. It should be, the key point is that it should be a tensor, which means that it depends on our variables, rho and v. But it depends on our variables, and it should have the tensor structure. And the only thing you can make is one of the things you can make is this structure, which we interpret momentarily. But there is also there is a pressure term which hangs around. So we have to incorporate this pressure term into the tensor.
So I guess the pressure is axial, so it should be along.
Wait. Why the pressure is axial? The pressure is here. Look at this and tell me what the pressure is. It's not axial. So how the pressure transforms under by axial, I assume you mean what? Transformation under reflection, or?
Oh, I mean that it acts perpendicular to a surface.
But there's no surface in the equation.
Right, and so it should. Yeah, I was thinking it would be along the diagonal. So,
Yes,
yeah.
yes, you're right. That's actually the sign of real master, namely to come using wrong assumptions to come to the right conclusions. It's indeed this way, and when we take the derivative, it actually gives you this term. When you take d beta of t alpha beta, you get precisely this. Now let's interpret this. What's the interpretation of this term? You see, this all measures how the momentum in a given, you have the momentum in some volume, total momentum, and it changes with time. And it changes with time for two reasons, because there are two terms, and I want you to spell out the reasons. Let's start with this term. What it means physically. Why it appears, compare it with the term in the case of mass density. We have d alpha rho v alpha, and we can integrate this equation. We did this simple exercise, integrated over the volume. Then they say the mass inside the volume changes because of what? So we take d dt of the integral rho d3x in the volume. It's non-zero, and let's first what? So why it is changing in the first place?
because the density is non-uniform and
The fluid can flow out of the region. It just left the region. And so the interpretation of that's the amount of mass which per unit time flows out of the region, and you have to integrate it over the boundary, over this surface. And that's the essence of this equation. So basically here we had only one reason for the mass density to change, and this reason was that that the fluid goes out of the domain. Now let's think about this thing. Let's first of all, what do you think about this term? It was simply rho v alpha here, and it was just the amount of mass carried out in alpha direction. Now here we have the amount of momentum density carried in beta direction. So the first reason was simply that you have that the fluid, it's basically the same. The fluid goes out of the domain and it carries the momentum density. So the momentum density changes because of this effect first. But it also changes for the other reason, which was not present. This part, as you see, is precisely analogous to this one. The only difference is that instead of rho with, well, let's call it beta, and instead of rho we substitute rho v beta, rho v alpha, the momentum density. So it was simple, just the same. And the second term is also simple. Why it appears in the first place? Well, it's, remember, momentum density, momentum changes because when you apply force. And this is simply the force applied to the given volume from the other parts of the fluid. So it just reflects the fact that you have internal forces in the fluid. And now we have to generalize this formula. This, as I said many times, this is the fluid is idealization. We assume it continues, but it's of course contains molecules which are interacting in some way, and the approximation which we are making is that we assume that the velocities are much smaller than the than the molecular velocities, and they change much more slowly than at the interatomic distances. So characteristic size at which velocities change, the gradients of the velocities, is assumed to be small. And that's why we could have, you see, that's why we actually have no gradients here. In principle, the energy momentum tensor could contain, it should be a tensor, and it could contain some derivatives of the velocity. But this is simply the first term of the Taylor expansion. Taylor expansion is also the gradient expansion, or derivative expansion. And now, it turns out to describe many phenomena, it's not sufficient to use the first approximation, but it's more or less sufficient to use the second approximation to this thing. And for that, we need to add to this T alpha beta, we need to add some terms with derivatives, which we assume still assume small. Velocities also assume small. Now so once again, we want to preserve the momentum conservation. So we want to preserve this equation. But we want to take into account that T alpha beta may be sensitive to the gradients of the velocity in the fluid. So we have T alpha beta of 0 approximation, which is this one, plus we have to find T alpha beta 1, which depends on the gradients. And since velocity is also assumed to be small with the molecular velocity in comparison with molecular velocity, we actually want it to be linear in velocities. We will keep it linear. So what is, let's try to think of what could it be, how it can look. Actually, it's a good way to attack some problem is just to try to imagine how the answer would look. So,
I'm sorry. Why did we say that the pressure term has to have only diagonal components? In general, if you have rotation like a torque, then
well, the pressure, you see, it's just it's basically that simple. You have the tensor T alpha beta, and we are interested in the term proportional to pressure. The pressure is a scalar. So what else? What kind of contribution, linear in pressure, you can get, which would be consistent with rotational symmetry? You see, there's nothing, but there's only one tensor, only one thing. You of course, you can also form something like that, gradients of pressure, but that's higher approximation. If you want the pressure without derivatives, the only way it enters into the stress tensor is, well, there's no other structure which can appear. See? So once again, when you construct the general the general expression for the stress tensor, this general expression must be consistent with rotational invariance of the equation. Do you see the point here? No? Well, it's important. So it's, I mean, this type of logic in physics appears again and again and again. So you have to really understand it and get used to it. So maybe you'll formulate your what puzzles you.
So I just don't understand how for rotation symmetry it's absolutely necessary to have this.
It's the only other type of contribution which is consistent with rotation symmetry basically means that the tensors must be equal to tensors. You cannot equate a tensor to I don't know, to a vector or so that's okay. Let's discuss it after. Maybe it's actually getting late a little bit. But anyway, the last point I want to make, which we will expand next time. So what if we talk about the velocity gradients? It's the same, by the way, the same thing, the same type of question which you asked. In what form it can appear in T alpha beta? So this first approximation, which is the linear ingredients. So give me at least one example of the expression which depends on velocities and contributes to the stress tensor. Just any term. And it should be consistent with rotational symmetry. Try something. What can you do with velocities?
You can take a Laplacian.
Okay, you can take a Laplacian, that's okay, but then the index, what you see, if you take a Laplacian of the velocity, there is only one index, it's a vector, and we need a tensor. So you what?
D beta V alpha.
Good. That's one of the terms which we'll really need. Yes. Well, something more. Since
D alpha V beta.
okay. And something more.
D beta, D beta?
What?
D beta, D beta?
But again, how about indices? You see, they will feel very lonely, those indices. There is one thing which you have at your disposal, which is written on the blackboard, which you can use, which is the Kronecker symbol. And this is the nice tensor expression. Okay, we will continue next time with it. And that's basically, we will see that C1 is equal to C2 because of some physical requirements, and that would be the answer. And that would give us viscous equation. Okay, let's stop here.